Hey guys, this is Josh with Group 5 for CHEg 4139, Section 1, and we're here today to talk about the 3D Reactors Lab. We're going to be taking a look at the theory behind this experiment, looking at how the mixing occurred in our printed 3D reactors, and taking you guys through the data collection techniques and analysis of our data.
The purpose of this experiment is to design a continuous microflow reactor with the assistance of SOLIDWORKS. The group investigated the effects of varying reactor parameters such as length of the microreactor and the flow rate into the device, and calculated the conversion at the reactor's end. From there, it could be modeled in COMSOL and the experimental conversions compared to the predicted conversions of COMSOL. COMSOL and SOLIDWORKS are both key elements of chemical engineering and crucial for industry use. The ability to design reactors to ideal specifications is a crucial skill, and combining the ability to model in SOLIDWORKS and predict in COMSOL, an engineer in industry can design a reactor and test it on site, and improve and test his design if needed. Microreactors play a key role when the objective is to synthesize materials faster than the standard batch techniques will allow for. These benefits will occur from the mass transfer that arises along with the high surface area to volume ratio common in most microreactors. Along with these factors, microreactors provide better energy efficiency, reaction speed, safety, and allow for ease of design and scalability since most can be made and manufactured on site. Therefore, microreactors are the preferred tools in hydrogen generation from fuel and bioreaction studies.
As far as safety goes, you need to make sure that you are wearing the correct PPE. A knee-length lab safety coat and protective lab safety goggles are required. Make sure to be covering all parts of your skin. A lab coat, long pants, and sneakers will prevent the sodium hydroxide and malachite green from contacting skin, while the goggles prevent the chemicals from contacting eyes. Flammability and reactivity of our two reagents is not a hazard for these experiments, but both malachite green and sodium hydroxide can be toxic in certain amounts and should be handled with care. This means wearing appropriate PPE and handling the reagents with care at all times.
For our system, there are 4 equations that will help determine how long the fluid needs to flow through the system, how long the system should be, and the conditions inside the system. The first of these equations, the Reynolds number, described as rho L U over mu, where rho is density, L is characteristic length, U is velocity, and mu is the viscosity of the fluid, describes the flow type of the fluid in the system. In a microfluid system, Reynolds number, Re, should be low, indicating laminar flow. The second equation, the Peclet number, described as L mu over D, where L is the characteristic length, mu is the viscosity of the fluid, and D is the diffusivity coefficient. The Peclet number in a micro device system such as ours should be high. The high Peclet number and low Reynolds number indicate one thing very clear. Mixing is not efficient in the system, and diffusion is the driving force of conversion in a microreactor. Knowing that diffusion is the driving force in our microreactor, 2 equations will help us determine our desired dimensions. The first one, known as T ideal, relates the Peclet number times width and the velocity of the fluids in the systems. This equation will tell us how long the Mg and the NaOH need to flow through the system in order to get the ideal time needed for complete conversion. The second equation, again relating the Peclet number, is just a multiple of the width. The equation Pe times W, being Peclet number times width, will tell us the ideal characteristic length of the reactor to determine how long the reactor should be to get the ideal time of the reactor. In order to overcome these flaws, we need to overcome the low mixing that is characteristic in these reactors. In order to do that, we need to maximize the diffusion. 2 simple ways of doing this are increasing the length or adding baffles. The final 2 equations, the residence time equation equal to volume over volumetric flow rate, and the first order PFR conversion equation are key for defining our system. Increasing the length will see an increase in the residence time due to the increase in volume, ideal for our system as it maximizes diffusivity. Knowing this, using our final results in the values we know for Ca0 and Cf, we can solve for X conversion.
Hey guys, I'm going to be walking you through the SOLIDWORKS designs for our reactors as well as the COMSOL simulations that we ran on those reactors. So you can see here that we pretty much followed the lab procedure to the letter in the design of our reactors. We've got each side length of the reactor being 50 millimeters across. We can see from this sketch that the diameter of our channels was kept at a near constant 3 millimeters for each reactor. We have stability tabs right here that extend 3 millimeters into the reactor, and the reactor itself is 6 millimeters high with a channel occupying the middle 2 millimeters. The reactor designs that we tested were our first custom design, which was a serpentine reactor with baffles, our pretzel reactor, which had just a bunch of baffles and a straight channel, our final serpentine design with even more curves than the first, and our basic T reactor. Now to walk you guys through the COMSOL simulation. First of all, you want to go to the import screen. You want to choose a mesh or STL file for here. You want to go into the computer files and you want to locate the channel that you're going to be testing in COMSOL. Once you've done that, it's time to get things set up. For materials, we're going to be using water, liquid as our model. You're going to want to set some things. For example, the 2 inlets on your reactor, the outlet on your reactor, the inflow, which contains the concentration of the reactants that are going to be entering your reactor, 0.5 mole per meter cubed for malachite green and 100 mole per meter cubed for sodium hydroxide. You're going to want to enter the kinetic data that you are given. You're going to want to take a look at the diffusivity that we were given, and we're going to, of course, have to enter the rate constant for this reaction. Having done that, you can apply your mesh, use the finest size available for the best results, although it will take longer to perform the COMSOL simulations. When we performed our COMSOL simulations, we were only able to get results for our 10 milliliter per minute trial. Our 15 milliliter per minute and 19 milliliter per minute trials were not able to get us any results despite using the finest mesh available.
The microreactors were designed in SOLIDWORKS and were then 3D printed. We clamped the reactors to a stand and made sure that they were level. We attached both inlets for the malachite green and the sodium hydroxide. A photocell with an LED was attached to the outlet of the reactor in order to get readings through the Arduino. These readings gave us the amount of light that passed through the photocell. Syringes of malachite green and sodium hydroxide were filled to 60 milliliters and were then put onto the syringe pump. The flow rate was set and then the pump was started. We then proceeded to collect said readings. The group assumed that a longer reactor length, increased pecklet number, and baffles would result in the highest conversion of malachite green. From this graph, we can see that the best converting reactor was the S reactor, followed by the serpentine reactor, the pretzel reactor, and finally the T reactor. All of the reactors had the same average channel length and height. Comparing the best and worst reactors, we find that the S reactor was 75 millimeters long, had baffles, and had a maximum pecklet number of 2,200, while the T reactor was 35 millimeters long, had no baffles, and had a maximum pecklet number of 1,100. When comparing each reactor to itself, residence time is a clear factor that increased conversion. The slowest flow rates resulted in the highest conversions and the longest residence time. This is evident in each reactor as conversion increases with residence time. Volume is also correlated to conversion. This is the most evident when comparing the T reactor, pretzel reactor, and S reactor. The pretzel reactor increases very slightly from the T reactor, and then the S reactor dominates due to its much higher residence time. This is caused by its higher volume. From this graph, we can tell if COMSOL predictions are close to our experimental values. There should be a 1-to-1 correlation. That is the reason that there is a 45-degree line going through the graph. We discovered that the T reactor and the S reactor were the closest in experimental values to COMSOL prediction. We attribute this to their simple designs. The serpentine reactor was off the most, and we were not able to model the pretzel reactor. This was due to its complex geometry. We assume that complex geometries will not result in accurate COMSOL predictions due to our troubles with applying mesh. Now we'll take a look at 3 reactors flowing at 15 milliliters per minute. Here we see the T reactor, which produced the lowest conversion of malachite green. The 2 reactants interact and begin to flow downward, but very minimal mixing occurs. In fact, almost all the mixing that is seen is due to the high flow rate. The pretzel reactor was our 3rd best reactor. We see a boundary layer form right before the pretzel between the malachite green and the sodium hydroxide. The boundary layer is slightly broken by the first diamond, but not by much. We only see malachite green mix into the sodium hydroxide stream and not the other way around. The boundary layer is still visible at the outlet of the reactor. The S reactor was the best due to its high promotion of mixing. We once again see a boundary layer form between the two reactants. The first chamber works to break this boundary layer up with baffles. It does a good job, as we can see the sodium hydroxide part of the boundary layer have a blue hue. The boundary layer is still visible, but not as distinguishable right after the chamber. Once the flow begins to hit the turns, the layer vanishes.
In conclusion, we can see that our first custom reactor design was our best reactor design, featuring a 70mm channel length and baffles, promoting the best diffusion of all our reactor types. The T reactor featured the worst diffusion among all of our reactors, with a small 35mm channel length and no baffles at all. This is in agreement with the limited COMSOL simulations we were able to run, as well as the theory for this experiment. The error bars for these experiments were constructed by taking 3 different trials run at the 3 different flow rates for each of the reactor types.